This video is about the ideal gas law. So before we get into the ideal gas law, let's take a look at our basic gas laws and then we'll transition in. Our basic gas laws, you want to be able to draw graphs for them, just basic graphs, or be able to look at basic graphs and determine what gas law it's showing. So my first one, I have volume and pressure. Okay, I know that volume and pressure are changing and my temperature is constant, so that tells me that this could be a Boyle's law equation. Then I look to see if it's directly proportional or indirectly proportional. With a high volume, I have a low temperature or a low pressure. With a high pressure, I have a low volume. So they're indirectly proportional. So I can make my assumption of what that graph is. Then, my next one, I have volume and temperature. Therefore, pressure is held constant. If pressure is held constant, that means that it must be a Charles law equation. I look at my beginning, and I have low volume, low temperature. At the end, I have high volume, high temperature. So therefore, the volume's small, so is temperature, and as volume increases, so does temperature. Therefore, they're directly proportional, and then I can make my assumptions to determine which gas law that represents. My third one, I have volume and pressure. Again, I look and I say my temperature is held constant, so it could be a Boyle's law equation. At the beginning, I have low volume, low pressure. At the end, high volume, high pressure. So this would show that they're directly proportional, and I would see if that fits any of my gas laws. And then finally, I have pressure and temperature, so I have volume held constant. At the beginning, I have a low pressure, low temperature. At the end, a high pressure, high temperature. So that shows me that they're directly proportional. And I look to see if I have a law that has volume constant with direct proportionality between pressure and temperature. So you should have gotten that A is Boyle's law, B is Charles' law, C is none of the laws, and D is Gay-Lussac's law. Okay? Notice that the only variables for these is pressure, temperature, and volume, nothing else. So there are a few flaws with our combined gas laws or our basic gas laws, and that is that it assumes the amount of gas is constant. Okay? We know that that's not always the case. So what if we want to know the number of moles? We want to know about the amount of gas that we have. We know that 1 mole of gas is equal to 22.4 liters, but this is only at STP, standard temperature and pressure, which is 273 Kelvin, 101.3 kilopascals. So my ideal gas law comes in, and this is where I can predict the moles of the gas when I'm not at standard temperature and pressure. My equation for the ideal gas law is PV equals nRT, known lovingly as PIV-NERT, and that is how you remember your ideal gas law. PIV-NERT, PIV-NERT. Okay? Let's go through the variables. I have P, which is pressure. Pressure is in atmospheres, kilopascals, millimeters of mercury, or torr. I have V, which is volume. That can be measured in liters. Normally liters. If you're given milliliters and centimeters cubed, you want to convert them to liters. Remember, there's 1,000 milliliters in a liter. N is your moles of gas. Remember, we can find moles of gas from grams using the molar mass. T is your temperature, must be told in Kelvin, thanks to the kinetic molecular theory. And R is going to be our ideal gas constant. Okay, this is one number, it's a given number, and we're going to explore what that number is. But we need that to balance out our equation. So what is R, our ideal gas law constant? Well, it's experimentally determined. This was determined by being able to plug in standard temperature, pressure, standard volume at standard temperature and pressure, 22.4 liters, with 1 mole for PV, T, and N. So at this time, if you would plug in to our equation here, solving for R, we're going to plug in 22.4 for V. We're going to plug in 1 ATM, or you can plug in 101.3 kilopascals, or somebody in your group can plug in 760 millimeters of mercury or 760 torr. So at this time, have each person in your group decide which person is going to pick which form of pressure. Okay, now that everybody has their own pressure, we're going to continue on, each person solving for their gas law constant. So like I said, each person is going to use 22.4 liters. You've picked your pressure. You're going to put 1 in for our moles of gas, and you're going to put in 273 Kelvin for your temperature. Take a moment to solve for R. Once you've solved, each person in your group is going to explain or tell the other members what they got and what their units are on R. That's very important. Okay, you should have been able to determine that if you have the units of atmospheres, your R value is 0.0821 atmosphere liters per mole Kelvin. So ATM liters is on the top, mole Kelvin is on the bottom, it's a fraction. If you use kilopascals, you should have got 8.31 kilopascal liters per mole Kelvin. And if you use millimeters of mercury or torr, you should have got 62.4 millimeters of mercury times liters divided by moles times Kelvin, or torr liters per mole Kelvin. Notice that all 3 units for pressure are different, and even 4 if you count in torr. So when you're doing these problems, you need to choose wisely. So let's go through an example. Okay, example number 1. We're going to calculate the volume that a 0.323 mole sample of gas will occupy at 265 Kelvin and a pressure of 0.900 atmospheres. First step is we're going to record our variables. We are starting with an N, a number of moles of 0.323 moles. We're starting with a temperature of 265 Kelvin, a pressure of 0.900 atmospheres. We are solving for volume, so volume is what we don't know. Next, we're going to choose an R value based on our pressure units. Our pressure units are atmospheres, so we need to choose to use 0.8 or 0.0821 atmosphere liters per mole Kelvin. Then we'll write out our equation and rearrange for V. So my Pivner equation's here. I rearrange for V, so V is nRT divided by P. Step 4, I'm going to plug and chug, remembering to use my units. So I plug in my value of my moles of 0.323 moles times my R value for R, my 0.0821 atmosphere liters per mole Kelvin, times my value for temperature, 265 Kelvin, divided completely by 0.900 atmospheres. I then go ahead and I cancel out my units to determine what are my final units on volume and to double check myself. My moles cancels out with moles in my R value. My atmospheres cancels out with atmospheres in my R value. My temperature units of Kelvin cancel out with my temperature units in my R value. And I'm left with liters. So I'm able to find that my gas has a volume of 7.81 liters. Now go ahead and try your ideal gas law worksheet number 4, problem number 1. You're going to set it up the same way, following the same steps, and you should get an answer of 0.0208 moles of gas.